Welcome viewers. In this video, we'll see the capacitance, definition, derivation and the problems. First we'll see the capacitance. You know that capacitance is nothing but it is formed using two conducting media with an insulator in between them. So the capacitor is a storage element. It is nothing but there are two conducting mediums are available. In between, insulating material will be presented. So the two conducting media with an insulator is called as a capacitor, right? First we will see the capacitance of parallel plate capacitor. There are various types of capacitors available. First we will see what is the expression for capacitance in case of parallel plate capacitor. So this parallel plate capacitor is shown in the diagram. So this is the two plates are available. Plate 1 and plate 2 parallelly it is placed. The dielectric is available in between the parallel plate. So the V is the applied voltage between the parallel plate and the distance between these two plates is d meters. Right? The parallel plate is available, applied voltage is V, the distance between the plate is d. Here the dielectric materials are available. So first we will see the derivation. So based on the Gauss law, the electric field intensity is given as E equal to Q divided by A epsilon. That is Q divided by 4 pi epsilon r square. That 4 pi r square is taken as A, so that it is Q divided by A epsilon. You take this equation number 1. And also in general, the electric field intensity is given as V divided by D, potential divided by distance. Right? So take this equation number 2. Right? From equation 1 and 2, so both are same. Equation 1 and 2 both are electric field intensity, so that we can equate this side. This side can be verified because both expression is for the electric field intensity. So from equation 1 and 2, so V by D equal to Q by A epsilon. Right? From equation 1 it is Q by A epsilon, equation 2 V by D. So both are equated. Now we substitute that Q equal to CV. You know that the general formula Q equal to CV. So that V by D equal to CV divided by A epsilon. Right. So this V got cancelled. Right. Bring this term in the numerator. Right. So that A epsilon by D equal to C. So that can be written as C equal to A epsilon by D. That is a very general formula. C equal to A epsilon by D. Right. So that is. So from the above expression, this capacitance is directly proportional to the area of the plate and inversely proportional to the distance between the conductors. Right? So what is the meaning? If you increase the area of the plate, the capacitance will increase. Similarly, if you decrease the distance between the plate, the capacitance will increase. Right? So it is A epsilon by D, the general formula. Now we'll see the capacitance of parallel plate capacitor, two media, that is two conducting media, two dielectrics. Right? Previously what we discussed is only one dielectric. Right? So refer this diagram. So this is the parallel plate. Two plates are available. In between the dielectric material is filled, but the only the portion of the dielectric is epsilon R1. First dielectric with epsilon R1. We have another dielectric with epsilon R2. Right? The two different dielectrics are available between this parallel plate. Epsilon R1. The dielectric, the permittivity of the first dielectric material is epsilon R1 and the second dielectric material is epsilon R2. The thickness is D1. This will be D2. Right? The applied voltage is V. Total voltage applied across the parallel plate is V. That is the drop across the first dielectric material is V1. Second one will be V2. Right? So we have D1, D2. Voltage is V1, V2. The permittivity will be epsilon R1 and epsilon R2. Right? So we'll go to the derivation. So the applied voltage V equal to V1 plus V2. Right? Voltage across the first dielectric material plus voltage across the second dielectric material. Right? So that is equal to V equal to, we know that E equal to V by D. From that V can be written as E into D. Right? So that E1 D1 plus E2 D2. Based on the formula, we know that E equal to V by D, so that from that we can write V equal to E into D, right? Now this E can be replaced as Q divided by A epsilon. The general formula for electric field intensity is Q divided by A epsilon 1. Due to E1, it is Q divided by A epsilon 1 into D1. This E2 is replaced as Q divided by A epsilon 2 into D2. Right? So the Q by A is commonly available in both the terms. So that is taken outside. So that what we have, d1 divided by epsilon 1 plus d2 divided by epsilon 2, right? Q by A is taken outside. Now we'll substitute Q equal to CV, right? The charge, the Q equal to CV, we will substitute here, we will replace this Q equal to CV, so that this V got cancelled, right? Now we bring this term in the numerator and bring this term in the denominator, so that A equal to C equal to A divided by D1 divided by epsilon 1 plus D2 divided by epsilon 2, right? So now we got the expression for capacitance. Now this epsilon 1 is nothing but epsilon 1 can be written as epsilon naught into epsilon r1. Similarly, epsilon 2 is epsilon naught into epsilon r2. That is absolute permittivity and relative permittivity. So this absolute permittivity is a common. This relative permittivity depends upon the material. First dielectric, and this one will be second dielectric, right? So this epsilon naught can be taken common. This epsilon naught is available in both the terms. So 1 divided by epsilon naught, it will go into the numerator. So that A epsilon naught divided by d1 divided by epsilon r1 plus d2 divided by epsilon r2, right? So this is the expression for capacitance with two different dielectric material. Now we'll see the problem based on this capacitor with two dielectric material, right? We'll see the statement. A parallel plate capacitor consists of two square metal plates of side 500 mm, right? The area of the parallel plate is 500 mm. The side, the one side is 500 mm and is separated by 10 millimeter, right? The distance between the two plate is 10 millimeter. In this, the Teflon is available with epsilon r equal to 2 for a thickness of 6 millimeter. Out of 10 millimeter, 6 millimeter is available with a Teflon, the dielectric material called Teflon, with epsilon r equal to 2, and is placed on the lower plate having a air gap of 4 millimeter. So the remaining 4 millimeter will be air gap. So total 10 millimeter. Out of 10 millimeter, 6 millimeter is Teflon with epsilon r equal to 2. Remaining 4 millimeter will be air gap, right? The voltage applied is 100 voltage. 100 voltage is applied. We need to find capacitance, displacement density, electric field intensity, and voltage in both Teflon as well as air. We need to find all these parameters for Teflon as well as air, right? Now we'll see the given data. What are the data given? So the area, the side is given 500 millimeter. So the area will be 500 into 500 millimeter square, right? Side into side. So millimeter square is converted into meter square. It is multiplied by 10 to the power minus 6. So 500 into 500 into 10 to the power minus 6 meter square, right? The distance d1, thickness of the first dielectric is 6 millimeter, that is 6 into 10 to the power minus 3 meter. The thickness of the second dielectric, that is air, is 4 millimeter, that is equal to 4 into 10 to the power minus 3 meter, right? So the epsilon r1 is given as 2 for the Teflon. The epsilon r1 value is given as 2. The epsilon r2 will be 1, that is air gap. For air gap, the value will be 1, right? The applied voltage is 100 voltage. Then epsilon naught, absolute permittivity, is 8.854 into 10 to the power minus 12. That we know that is a constant. So by using this, we will find the values one by one. First we will find the capacitance. So the capacitance with two dielectric is nothing but epsilon naught A divided by d1 divided by epsilon r1 plus d2 divided by epsilon r2, right? Now we'll substitute this value. Epsilon naught is 8.854 into 10 to the power minus 12, right? What is the area? 500 into 500 into 10 to the power minus 6, right? So this is first dielectric, right? First dielectric, the thickness is 6 into 10 to the power minus 3. The permittivity value is 2. Second dielectric, 4 millimeter, 4 into 10 to the power minus 3, that is air, so that the value will be 1, right? So by simplifying this, what we got? 3.16 into 10 to the power minus 10 farad, right? So first we calculated the value, capacitance value is calculated for this two dielectric material. C will be 3.16 into 10 to the power minus 10 farad. Now we need to find the remaining values: displacement density, electric field and potential. So before that, value of charge density in plate 1 and 2 is same, since the charge and area of the plate 1 and 2 are same, right? That means the displacement density will be equal for both the cases, because the charge density in plate 1 and 2 are equal, so that the area of the plate 1 and 2 also equal. Now we'll find the remaining value. Capacitance value is calculated. Now we'll see the displacement density. That is nothing but Q divided by A. Displacement density is nothing but Q divided by A. So that is Q is replaced by CV divided by A. Q equal to CV divided by A, right? The displacement density is nothing but displacement per unit area. So based on that, Q by A, Q is replaced by CV divided by A. Now we'll substitute this value, C. Now we calculated this C value, capacitance 3.16 into 10 to the power minus 10. The applied voltage will be 100. What is the area? 500 into 500, 10 to the power minus 6, right? We will substitute all the value. So it is better to take 5 to 6 decimal, so that the answer will be very accurate. Normally, if you take the 6 digit after the decimal, the answer will be very nearer, right? So 0.001264 into 10 to the power minus 4 Coulomb per meter square, right? This displacement density, right? We are taking 6 decimal and also 10 to the power minus 4 also available, right? So from this D value we can find E1 and E2. So E1 equal to D1 divided by epsilon naught into epsilon R1. We know the relation between D and E, right? So D equal to epsilon E. From that, E equal to D by epsilon, right? So the D1, D2 is there, both are equal. D1, D2 are equal to D. So D value is 0.001264 into 10 to the power minus 4. Thus we calculated, divided by epsilon naught, that is constant, 8.854 into 10 to the power minus 12. Epsilon R1 value is 2, right? So by simplifying, what we got? 7138.02 voltage per meter. Nearly it is 7000. 7138.02 voltage per meter. Similarly, we can find the E2 value. E2 equal to D2 divided by epsilon naught into epsilon R2. So the D2 also same. 0.001264 into 10 to the power minus 4. That is available here. Divided by epsilon naught is constant, 8.854 into 10 to the power minus 12. Epsilon R2 is 1 because of air medium. So by simplifying this, what we got? 14,276.03 voltage per meter, right? So now we got the value of V1 and E2. From that we can find V1 and V2. So V1 equal to E1 into D1, that is E equal to V divided by D. From that, V equal to E into D. So the E1 value we calculated. E1 value is 7138.02 into the D1, the distance. The first dielectric will be 6 into 10 to the power minus 3, 6 millimeter. So what we got? 42.83 voltage. Similarly, V2, E2 into D2. So E2 we calculated 14,276.3 voltage per meter into D2. D2 is the air gap, 4 millimeter. 4 into 10 to the power minus 3. So by simplifying this, what we got? 57.10. So V1 will be 42.83, V2 will be 57.10. So by adding these two, what we got? 99.93 voltage. That is the applied voltage is 100. We know that applied voltage. So by adding, it is nearly we got 99.93. So the value what we got calculated is almost correct. It is nearer to the 100 voltage. That's why we are taking the displacement density as a 5 to 6 digits, right? So now we calculated capacitance, then displacement density E1, E2, V1 and V2. So all values are calculated. Now we'll go to the one more problem. So in the second problem, the capacitance value is given, that is 2 into 10 to the power minus 10 farad. The capacitance of a condenser formed by two parallel plates. The area is 100 centimeter square and separated by 2 millimeter. For this, the value will be 2 into 10 to the power minus 10 farad. Right? So the area of the plate is available, the thickness, the distance between the plate is available, and the capacitor value is available. The potential applied is 20 kilovolt, 20 kV. Right? We need to find the value of charge, electric field intensity and relative permittivity. We need to find these three values. Right? First we will see the given data. So the area is given 100 centimeter square. While converting into meter square, we need to multiply 10 to the power minus 4. So the area is 100 centimeter square. That is equal to 100 into 10 to the power minus 4 meter square. The applied voltage is 20 kV. 20 kV means 20 into 10 to the power 3 voltage. Kilo voltage means we need to multiply with 10 to the power 3. The distance between the plate is 2 millimeter. That is equal to 2 into 10 to the power minus 3 meter. Millimeter to meter means we need to multiply with 10 to the power minus 3. The capacitance value also given, C equal to 2 into 10 to the power minus 10 farad. Right? So these are all the given data. From that we can find the values one by one. First we will find the charge. Charge Q equal to CV, very standard formula. Q equal to CV. So that C value is given 2 into 10 to the power minus 10. The voltage is 20 kilovolt, 20 into 10 to the power 3. So multiplying these two, what we got? 40 into 10 to the power minus 7 coulomb. The charge will be 40 into 10 to the power minus 7 coulomb. Then we will find the electric field intensity, E equal to V by D. These two values are available, voltage available, distance available, so that we can use this formula, right? V by D. So V equal to 20 kilovolt, 20 into 10 to the power 3 divided by the distance is nothing but 2 millimeter, 2 into 10 to the power minus 3, that is equal to 10 into 10 to the power 6 voltage per meter. Right? The electric field intensity will be 10 into 10 to the power 6 voltage per meter. Now we need to find one more value, that is permittivity, relative permittivity. That is from this formula we can find C equal to epsilon naught epsilon R A divided by D. It's a very standard formula. In this C is available, epsilon naught is available, area available and distance also available. Right? So cross multiply and simplify this expression so that epsilon R equal to C into D divided by A into epsilon naught. Right? So because we need to find epsilon R, so it is rearranged such a way that epsilon R equal to C into D divided by A epsilon naught. Now substitute the C value. C is 2 into 10 to the power minus 10. The distance is 2 millimeter, 2 into 10 to the power minus 3. The area is 100 into 10 to the power minus 4 meter square. Then epsilon naught value is 8.854 into 10 to the power minus 12. Now all the values are substituted. By simplifying, what we got? 4.517. Right? So in this problem we calculated the charge value, electric field intensity and the capacitance. From this capacitance we calculated relative permittivity. Right? So in this video we discuss about the capacitance definition, derivation and two problems. Welcome viewers. In this video we'll see the capacitance of a cylindrical capacitor or cable, the derivation and the derivation for this cylindrical capacitor or cable. Both are equivalent, right? First we'll see the diagram. So we have the cylindrical capacitor. The cylinder is available with inner and outer radius are A and B respectively. We have two cylinders are available. The radius of inner and outer cylinder is A and B. The space between the cylinder is filled with the dielectric having the permittivity of epsilon r, right? Now see this, refer this diagram. So this is the inner cylinder with radius A. This is the outer cylinder with radius B, right? We have taken the 1 meter length of the cylinder, right? So the inner cylinder radius A, outer cylinder radius B, and the height of the cylinder is 1 meter. For calculation purpose, we consider one Gaussian cylindrical surface with radius rho meter. Gaussian cylindrical surface with rho, that is in between A and B. In between A and B, one imaginary Gaussian cylindrical surface is taken, that is the radius is rho meter, right? We'll see this description. So it is required to determine the capacitance per meter length. First we'll find the capacitance per meter length. The total capacitance will be capacitance per meter length and multiplied by length of the capacitor, right? That is given here. So we consider the Gaussian cylindrical surface with radius rho meter and height 1 meter, right? The cable acts as a cylindrical capacitor. This is the underground cable, this, right? That is equivalently we are treated as a cylindrical capacitor. Underground cable having two conductors, inner conductor as well as outer conductor. In between the insulator is available, right? So this is treated as a underground cable or cylindrical capacitor. Now we'll see the derivation for this cylindrical capacitor. First we will find the electric field intensity, then voltage. From that we can find the capacitance. The electric field intensity E equal to Q divided by 4 pi epsilon r square. That is a very general formula. Q divided by 4 pi epsilon r square. That is rewritten as epsilon Q divided by epsilon into 4 pi r square. What is this 4 pi r square? This is nothing but a area of a sphere. Normally all the charges what we assumed as a spherical form, sphere, 4 pi r square. But here we are going to find the cylindrical capacitor. We are assuming that the charges available in the cylindrical capacitor, so that the area of the sphere is replaced by area of the cylinder, 2 pi RH. Area of the cylinder is 2 pi RH, right? In this 2 pi, R is nothing but rho. We assume a cylindrical capacitor with radius rho and the height will be 1 meter. So H is replaced as 1. So that it is nothing but Q divided by 2 pi epsilon into rho. The electric field intensity, especially for a cylindrical capacitor, will be Q divided by 2 pi epsilon into rho, right? From this we can find the potential difference. So what is the potential difference between the two cylinder? Is the work done in moving a unit positive charge from outer cylinder to inner cylinder, right? The unit charge is moving from outer cylinder to inner cylinder, so the limit is from B to A. That is nothing but radius of the outer cylinder to radius of the inner cylinder, B to A, right? So we know that V equal to potential V equal to minus integral B to A E into d rho. That is a general formula for the potential in terms of electric field, right? V equal to minus integral E dot d rho. We consider rho meter radius, so that it is d rho, right? So that is equal to minus integral B to A. Q is replaced as Q divided by 2 pi epsilon into rho, right, into d rho. In this Q divided by 2 pi epsilon is constant. Only we have integral. Now the negative sign is removed by interchanging the limit. Now the limits are interchanged. B to A is now given as A to B, so that we can remove this negative sign. 1 divided by rho into d rho, right? Q divided by 2 pi epsilon is constant. Integral a to b. B to a is now interchanged into a to b, so that we can remove this negative sign. 1 divided by rho into d rho, right? So the 1 divided by rho. So Q divided by 2 pi epsilon. Integral 1 by rho is nothing but log rho with a limit of a to b. We need to substitute the limit a to b, so that v equal to q divided by 2 pi epsilon into log b minus log a. So upper limit and lower limit, while substituting we got minus log b minus log a, right? So what we got, v equal to q divided by 2 pi epsilon log b minus log a. But what we need is capacitance. So that substitute q equal to Cv. In this equation we are replacing q equal to Cv. That is v equal to q. Q is Cv into divided by 2 pi epsilon. Log b minus log a is written as log b by a. Right? So this v got cancelled. Bring this term in the numerator. Bring the log b by in the denominator. Right? 2 pi epsilon is brought into numerator. Log b is brought into denominator. So 2 pi epsilon divided by log b by a equal to c. Right? So that can be written as c equal to 2 pi epsilon divided by log b by a. Right? So that is nothing but the unit is farad per meter. Right? Here we consider only 1 meter length of cable. So the unit is nothing but farad per meter. 2 pi epsilon divided by log b by a. Suppose if we want to find the total capacitance, here we consider only 1 meter length of cable, underground cable. If you want to find the entire length of the cable, C total equal to 2 pi epsilon log b by a into L. It is multiplied by the length of the capacitor, so that unit will be farad, right? So it is 2 pi epsilon divided by log b by a into L. The unit is farad. So in this video we discuss about the cylindrical capacitor, the derivation. We got the expression for capacitance of a cylindrical capacitor. So this is nothing but a underground cable, right? Capacitance per meter as well as total capacitance also we got the expression. Welcome viewers, in this video we will see the capacitance of a spherical capacitor, the derivation and one problem. So the spherical capacitor is shown in the diagram, right? So we have inner sphere and outer sphere. In between the dielectric is filled. So the radius of the inner sphere is a meter. Radius of the outer sphere will be b meters, right? The charges are accumulated, positive charges and negative charges. So this inner sphere and outer sphere in between the dielectric is act as a capacitor. Now we'll see the expression for this, the spherical capacitor. So the description is given. The radius of inner and outer sphere are a and b respectively. The space between the two spheres are filled with a dielectric with a permittivity epsilon r. So our aim is to find the capacitance between inner and outer sphere. So we start with the electric field intensity, then we'll go to potential, then we'll find the capacitance. The electric field intensity is given by E equal to Q divided by 4 pi epsilon r square. That is the general formula. Here we can take as it is, right? So the sphere, we consider the sphere, so E equal to Q divided by 4 pi epsilon r square is taken. The potential is given by the relation between potential and electric field, V equal to minus integral E dot dr. So this dr is nothing but in between inner and outer sphere. We consider one radius in between inner and outer sphere. Now we'll see what is the limit for this integration. What is the limit? So the potential difference is the work done in moving a unit positive charge from negatively charged sphere to positively charged sphere, right? Here the potential, the work done is nothing but moving a unit positive charge from negatively charged sphere to positively charged sphere. That is the It is from the outer sphere to inner sphere, so that the limit are from B to A, the radius of the outer sphere to radius of the inner sphere, right? So the limit is from B to A, so that V equal to minus integral B to A E dot dr, right? Now substitute the value of E equal to Q divided by 4 pi epsilon r square into dr. The limit is now the limit is interchanged. B to A is now interchanged with A to B, so that this negative become positive, right? So Q divided by 4 pi epsilon is now constant. Only we have integral B A to B 1 divided by r square into dr, right? So Q divided by 4 pi epsilon, the integral 1 by r square is minus 1 by r. We know very well. So the integral 1 by r square is minus 1 by r. Substitute the limit A and B. So that Q divided by 4 pi epsilon. So this limit minus 1 by B. So while substituting lower limit, already one minus is there. We'll go one more minus. So it becomes plus 1 by A. Right? So that can be rewritten as V equal to Q divided by 4 pi epsilon 1 by A minus 1 by B. It is rearranged. Now we'll take the LCM. Q divided by 4 pi epsilon. Take this LCM AB. So here B will be multiplied here. A will be multiplied here. So B minus A divided by AB. V equal to Q divided by 4 pi epsilon B minus A into AB. But what we need is capacitance. So substitute Q equal to CV. Replace this Q by CV. So that V equal to CV divided by 4 pi epsilon B minus A divided by AB. Right? This V got cancelled. Bring this term in the numerator. Bring this term in the denominator. So 4 pi epsilon divided by B minus A divided by AB is again go to the numerator. So 4 pi epsilon AB divided by B minus A equal to C. So that can be written as C equal to 4 pi epsilon AB divided by B minus A. So this is the expression for spherical capacitor with radius A and B. It is 4 pi epsilon AB divided by B minus A. Now we'll see one problem in the spherical capacitor, right? The radius of two sphere differ by 4 centimeter. The radius of inner and outer sphere is not given, but the difference between inner and outer sphere is given as 4 centimeter, right? The capacitance of this spherical capacitor is 53.3 picofarad, right? The capacitance value is given 53.3 picofarad. If the outer sphere is earthed, calculate the radius A and B assuming air as a dielectric, right? So the capacitance value is given. The A and B values are not given, but difference between A and B values is given as 4 centimeter. Now we need to assume air dielectric. So with this given data, we need to find what is the radius of inner radius and outer radius A and B, right? So first we will see the given data. The difference between these two is B minus A equal to 0.04, 4 centimeter. While converting into meter, 4 into 10 to the power minus 2, that is nothing but 0.04 meter. The capacitance value is given 53.3 picofarad, that is 53.3 into 10 to the power minus 12. Picofarad means 10 to the power minus 12 farad. Then epsilon naught value is constant 8.854 into 10 to the power minus 12. Epsilon r equal to 1 because it is given as air as a dielectric, right? What is the expression for spherical capacitor? C equal to 4 pi epsilon AB divided by A minus B. Just now we got this expression, right? So in this what we need this AB, because A minus B also known value. So we bring this term here and bring the 4 pi epsilon in the denominator. So C into A minus B divided by 4 pi epsilon equal to AB. Right. So that AB equal to C into A minus B divided by 4 pi epsilon. This epsilon is written as epsilon naught into epsilon r. Right. Now substitute all the values. C is given as 53.3 into 10 to the power minus 12 into the difference between these two is 0.04 divided by 4 pi. Epsilon naught is 8.854 into 10 to the power minus 12. Epsilon r value is 1. Right? So by simplify this, what we got? 0.0192. Right? The AB value after simplification, what we got? 0.0192. But we know that B minus A equal to 0.04. From that, B equal to 0.04 plus A. Bring this A in this side. So that B equal to 0.04 plus A. Right? So now AB equal to 0.0192. So in this, you replace this B. B equal to 0.04 plus A. Right? This B is replaced as 0.04 plus A. That is equal to 0.0192. Right? So multiply inside. A is multiplied. So 0.04A plus A square equal to 0.0192. Right? So rearrange this so that A square minus this term is brought here, minus 0.0192 plus 0.04A. Right? So while rewriting A square plus 0.04A, this A is available, 0.04A minus 0.0192. So this is a quadratic equation. The A value is 1, B value is 0.04, C value is minus 0.0192. Right? So this the A value can be calculated from this general formula. Minus B plus or minus B square minus 4AC divided by 2A. Right? So this B value is nothing but 0.04 minus, already one minus is there, plus or minus. B square is 0.04 square minus 4 into A. A value is 1. That C value is minus 0.0192 divided by 2A. 2 into A. A value is 1. Now we need to simplify this expression. So that is simplified 0.04 plus or minus 0.04 square plus 0.0788. Right? So after simplification, what we have? Minus 0.04 plus 0.018, the square of this value, and this 0.0768 divided by 2. Right? Now both the values are added together. 0.04 plus or minus 0.0784 square root. So while taking the square root, what we got? Minus 0.04 plus or minus 0.28 divided by 2. Now we can divide by these two. So 0.04 plus or minus 0.28 divided by 2 can be written as minus 0.02 plus 0.14. Right? So we can, two values are available now. Minus 0.02 plus 0.14, minus 0.02 minus 0.14. So while doing this, what we got? 0.12 and minus 0.16. These two values are possible, either 0.12 or minus 0.16. But the value will not be negative. The value will be positive, so that we can take A equal to 0.012 means 12 centimeter. 0.12 meter means 12 centimeter. B equal to 0.16 mean it will be 16 centimeter. Right? So A equal to 12 centimeter, B equal to 16 centimeter. See, the difference between these two is nothing but 4 centimeter. So what with the value what we calculated is correct. Right? So we calculated the radius of inner sphere and radius of outer sphere. Welcome viewers. In this video, we'll see the capacitance of two-wire transmission line. This is the overhead transmission line, having the two conductors, so the single phase power can be transmitted through this transmission line. It is a overhead transmission line. So by referring the diagram, we have the two conductors, conductor A and conductor B. Conductor A is positively charged and conductor B is negatively charged. Our aim is to find the capacitance between these two conductors, conductor A and B. The radius of the conductor is R meter. Radius of each conductor is R meter. The center to center distance between the conductor is D meter. The center of conductor A to center of conductor B is D meter. The point P is located. We are having the point P at a distance X meter from the center of the conductor A. The point P is available at a distance X meter from the center of conductor A. conductor A is taken as reference conductor. Then the distance between point P and center of the conductor B is d minus x, right? So this will be x, this will be d minus x. The distance between center of conductor A to outside of conductor B is d minus r. So during the integration, we need a limit. So the limit is decided by two parameters. One is radius of the conductor. Another one, this d minus r, center of the conductor A to outside of conductor B. So this distance will decide the another limit of the integration, right? So we have conductor A and B, center to center distance is d meter, radius is r meter. Point P is located at a distance x meter from the center of conductor A. The distance between point P and center of conductor B is d minus x. The point P is available. EA and EB is nothing but electric field intensity due to conductor A and conductor B. Now we are having the Gaussian cylindrical surface. We are assuming on Gaussian cylindrical surface with radius x meter. We are assuming that here one cylindrical surface is available, x meter, and the height is 1 meter. We are assuming 1 meter length of cable, right? So the Gaussian cylindrical surface with radius x and height 1 meter. Similarly, if you refer conductor B, we have another Gaussian cylindrical surface with radius d minus x, right? If you refer A, x, if you refer B, d minus x. So there are two conductors available, right? So the total capacitance, this is the total capacitance, is nothing but capacitance due to conductor A and capacitance due to conductor B. Both are connected in series, right? So this C dash is the capacitance due to conductor A. This C dash is capacitance due to conductor B, right? So due to both are connected in series, the total capacitance C is C dash dot C dash divided by C dash plus C dash. So that is equal to C dash dot C dash divided by 2 C dash. By adding these two, we got 2 C dash. So 1 C dash got cancelled. So the C dash divided by 2, right? So C equal to C dash divided by 2. From that, C dash equal to 2 into C. The capacitance per conductor equal to 2 times of total capacitance. C dash equal to 2C. So we will find both C as well as C dash, total capacitance as well as capacitance due to the conductor, per conductor. Here the description is available. The conductor A and B are uniformly charged with plus lambda by Coulomb and minus lambda by Coulomb respectively. Right? Conductor A is positively charged, conductor B is negatively charged. Due to length, we are using linear charge density, plus lambda and minus lambda. Radius of each conductor is r meter and separated by d meter. We are considering the point P at a distance x meter from the reference. Reference is nothing but conductor A. Then the distance between conductor B and point P is d minus x. EA and EB are the electric field intensity due to conductor A and conductor B. Now we'll apply the Gauss law to find the electric field intensity due to conductor A, right? By using Gauss law we will find. So we are having the imaginary cylindrical surface with height 1 meter and radius x meter. We consider one imaginary cylindrical surface. So the general formula for E equal to Q divided by 4 pi epsilon r square is the general formula. So that can be rewrite as Q divided by epsilon 4 pi r square. Since 4 pi r square refer the sphere. Normally we refer the charges are in the form of sphere. But here we are using cylinder. So that this term is replaced by area of the cylinder 2 pi RH. Especially in this derivation we are using cylinder. So that this term is replaced by 2 pi RH. In this r is nothing but x, the radius is x and the height is 1 meter. So that what we got Q divided by 2 pi epsilon x. So the electric field intensity for this cylindrical surface is Q divided by 2 pi epsilon x. For other cases we can use this directly, right? Because of cylinder, it is replaced by this value, q divided by 2 pi epsilon x. Now we have the two electric field available. So the total electric field equal to EA plus EB. Electric field due to conductor A plus electric field due to conductor B. So that is q divided by 2 pi epsilon x. That's available here. While referring conductor B, q divided by 2 pi epsilon d minus x, because the conductor B and the distance between the conductor B and point P is d minus x, right? So conductor A located at a distance x meter, conductor B located at a distance d minus x. Now this q divided by 2 pi epsilon is constant between these two, commonly available between these two, we can take outside. So what we got, q divided by 2 pi epsilon 1 by x plus 1 by d minus x, right? Now we got the expression for electric field. From that we will go to potential. From the potential we can find the capacitance. Then what is the relation between the electric field and potential? E equal to minus dV by dx. So that dV equal to minus E into dx. From that, by integrating on both sides, V equal to minus integral E dot dx. This is a standard formula. V equal to minus integral E dot dx. From that we can find the expression for potential. Now we'll see what is the limit for this integration. So the potential difference between A and B is defined as work done in moving a positive charge from B to A, right? So the potential difference is nothing but work done. For the what is work done? Moving a positive charge from B to A. So the electric field lies between the surface of conductor A and B, that is d minus R to R, right? The distance between the conductor outside d minus R and radius of the conductor R, that will decide the limit for this integration. So we are using the limit d minus R to R. So that V equal to minus, the substitute the limit d minus R to R, q divided by 2 pi epsilon into 1 by x plus 1 by d minus x into dx. Now these limits are substituted and E value is substituted. So this q divided by 2 pi epsilon is constant, that is taken outside, minus q divided by 2 pi epsilon integral d minus R to R 1 by x plus 1 by d minus x into dx. Now we can go for simplifying the this integration. So while simplifying, q divided by 2 pi epsilon is there. So the 1 by x, integral 1 by x is log x. Similarly, 1 by d minus x is log d minus x, but here minus x is available. Again we need to differentiate. Differentiating minus x is minus 1. If it is d plus x, no problem. D minus x is there. We are integrating with respect to x. So we need to take the differentiation of minus x again. So that will give minus 1. Right? With a limit d minus R to R. So integral 1 by x is log x. Integral 1 by d minus x is log d minus x. But here minus x is available. By differentiating this minus x, we are getting minus 1. Right? Now we can substitute the limit. Q divided by minus q divided by 2 pi epsilon log x. So this minus 1 become this minus negative. Minus log d minus x d minus R to R. Right? The term become minus. Now we'll substitute the limit one by one. Minus q divided by 2 pi epsilon. We substitute this limits. Log R minus log d minus R. First the upper limit is substituted. Log R minus log d minus R. Then substitute the lower limit. Minus. While substituting lower limit, we got minus. Minus log d minus R. Here already one minus is there, so it become plus log d minus this x. X is nothing but minus log d minus of d minus R. Right? This x is replaced by d minus R. Right? So log R minus log d minus R. Upper limit. Log d minus R plus log d of d minus R. This is lower limit. Right? This negative is there, so that it become positive. Now we can go for further simplification. So log r minus log d minus r minus log d minus r plus log, you can multiply inside, d minus minus d plus r, d minus d plus r. While multiplying this negative inside, what will happen? It become minus d. The already one minus is there, so it become plus r. So this d got cancelled. Right? Now what we got? Log r minus log d minus r minus log d minus r into this plus log r. Right? See this log r available 2 times. Log d minus r also available 2 times. So we can add these two values. So 2 log r minus 2 log d minus r. Right? Now we can take these two outside. Right? Already one 2 is there, so got cancel. Log r minus log d minus r. Right? So that what is there? Q divided by pi epsilon log d minus r by r. Log r. Right? So the negative available outside, that is multiplied inside, so that these two values are interchanged. This become negative, this become positive. So that log d minus r minus log r. Right? What is log d minus r minus log r? That is nothing but log d minus r by r. Log a minus log b is nothing but log a by b. By using that, we can find this. So that finally what we got? V equal to Q divided by pi epsilon log d minus r by r. Right? Now we got the expression for the potential. But our aim is to find the capacitance between the conductors. Right? Okay. So that we are substituting Q equal to CV. We are replacing Q by CV. So that V equal to, this Q is there. Q is replaced by CV divided by pi epsilon log d minus r by r. So this V got cancelled. Right? So bring this term in the numerator, bring this term in the denominator. So that C equal to pi epsilon divided by log d minus r by r. Right? So this term is brought into numerator. This term is brought into denominator. That is equal to C. Right? So what we got? C equal to pi epsilon log d minus r by r, the final expression. What is the unit? Farad per meter. Because we consider only 1 meter length of cable, so that the unit is farad per meter. Pi epsilon divided by log d minus r by r. So this is the total capacitance. What is the capacitance per conductor? C dash equal to 2 times of C. 2 times of total capacitance. Capacitance per conductor. So that is C dash equal to 2 times of this C. Right? 2 into C. 2 pi epsilon divided by log d minus r by r. Right? So this is the capacitance due to conductor, single conductor. So that unit is farad per meter per conductor. Only one conductor. Here we are, C dash refers only one conductor. Right? So 2 pi epsilon log d minus r by r farad per meter per conductor. Right? So this is total capacitance. This will be capacitance due to single conductor. In both the cases, we assume 1 meter length of cable. Right? Now we got the expression for total capacitance as well as capacitance due to single conductor. Now we'll solve two problems. First we'll go to the first problem. Right. In this first problem, calculate the capacitive reactance Xc of a single phase 50 Hz transmission line of 100 km with 2 parallel lines of 1 centimeter diameter wire with 3 meter diameter apart in free space. Right? So we need to find the capacitive reactance for a single phase transmission line. The frequency is 50 Hz. The length is 100 km, that is 100 into 10 to the power 3 meter. The distance between the conductor is 3 meter. The diameter is 1 centimeter, so that radius equal to 0.5 centimeter, that is 0.5 into 10 to the power minus 2, that is 0.005 meter. Right? Now these are the data available. Frequency available, length of the conductor available, distance between the conductor available, diameter, thereby radius available, epsilon naught is nothing but 8.854 into 10 to the power minus 12, right? That value also available. Now we'll find the capacitive reactance. If you want, the capacitive reactant formula is 1 divided by 2 pi Fc. Is a formula. Here F is already available, 50 Hz. But C value is not given. So first we will find the C value. If after calculating C value, we can calculate the capacitive reactance, right? What is C value? Pi epsilon naught epsilon r divided by log d minus r by r. Just now we got this derivation. This is a total capacitance, C. Pi epsilon naught. So the pi into epsilon naught is 8.854 into 10 to the power minus 12. Epsilon r is 1. We are assuming that it is a air. Divided by log d minus r. D is distance. Distance between the conductor is 3 meter minus radius is 0.005 meter divided by 0.005. Right? So this is a natural log. Base E. You have to consider the base E, not a base 10. It's a natural log. Into 100 kilometer. You have to multiply with the length of the conductor, right? 100 kilometer. So 100 into 10 to the power 3. So now all the values are substituted. The final C value is 0.434 into 10 to the power minus 6 farad. Now we got the value of capacitance. From that we can find, by using this capacitance, this formula, we can find the capacitive reactance. So the capacitive reactance Xc equal to 1 divided by 2 pi Fc, that is equal to 1 divided by 2 into pi into the frequency is 50 Hz. The capacitor value is 0.434 into 10 to the power minus 6. Right? After simplifying, what we got? The capacitive reactant Xc equal to 7.334 kilo ohm. Because of the reactance, it is given as ohm, kilo ohm. Right? That is 10 to the power 3. 7.334 kilo ohm, right? So for calculating capacitive reactance, we first calculated the capacitance. From that we calculated the capacitive reactance. Now we'll go to the one more problem. Two parallel long conductor have provided a capacitance of 20 picofarad. The capacitance value is given. This is also two-wire transmission line. The capacitance value is 20 picofarad. The center to center distance between the conductor is 1 centimeter. The center to center distance also given, 1 centimeter. What is the question? What size of conductor, what size of the wire should be used when epsilon r equal to 1? Right? What does size mean? Radius. We need to find the radius of the conductor when epsilon r equal to 1. First division. In the second division, what size of wire should be used if it is placed in a sea water? Through the transmission line is placed in a sea water. In that case, epsilon r equal to 2. Right? So first case epsilon r equal to 1. Second case sea water, that is epsilon r equal to 2. Right? So first we will write the data. So we are having the capacitance value 20 picofarad. 20 picofarad means 20 into 10 to the power minus 12 farad. The center to center distance is available 1 centimeter, means 1 into 10 to the power minus 2 meter, that is 0.001 meter, right? 0.001 meter. Then epsilon naught is constant 8.854 into 10 to the power minus 12. So these are all the data available. First we will consider the first case, epsilon r equal to 1, right? What is the formula? C equal to pi epsilon naught epsilon r divided by log d minus r by r. So just now we got the derivation, capacitance of a two-wire transmission line. So this r is the question. We need to find what is the size of the wire. Size of the wire means radius of the wire. Other data are available. Capacitor is available. 20 into 10 to the power minus 12 farad, right? It's not 2, it's 20. 20 into 10 to the power minus 12 by epsilon naught is 8.854. The epsilon r is 1 divided by log d minus r, 0.01 minus r by r, right? So now this r value we need to find. Bring this term here and bring this 20 into 10 to the power minus 12 in the denominator. So log 0.01 minus r by r equal to this value divided by 20 into 10 to the power minus 12, because this value is not known, we need to find. So by simplifying this, what we got? 1.39. So the log to the base e 0.01 minus r by r equal to 1.39, right? Then how will you find the radius from this expression? What is the how to find that? So here one example is available. Log base e a equal to x means that can be rewrite as, you have to interchange these two values. E power x equal to a, that is we are removing the log, right? For how to remove this log, we need to interchange these two values. E power x equal to a, so that we can remove the log value. E power x equal to a. Like that, you have to bring this value here. E power 1.39. Bring this value here. 0.01 minus r by r, right? So based on this formula, interchanging these two will remove the log. Here we are doing the same, we are using the same formula. E power 1.39 equal to 0.01 minus r by r, right? So e power 1.39 is 4.014, that is equal to 0.01 minus r by r. Now cross multiply this. 4.014 r equal to 0.01 minus r, right? Bring this r that side, so that 4.014 r plus r equal to 0.01. So these two are added. 5.014 r equal to 0.01. So r equal to 0.01 divided by 5.014. From that we calculated r equal to 1.994 into 10 to the power minus 3 meter. That is r equal to 2 millimeter. Right? R equal to, by using this we can find r equal to 2 millimeter. So first case, the radius of the conductor, size of the conductor is 2 millimeter. Now we'll go to the second condition, epsilon r equal to 2. Same problem, only we need to find, substitute epsilon r equal to sea water. C equal to pi epsilon naught epsilon r divided by log to the base e d minus r by r. The c value is substituted, epsilon naught is substituted, pi, the epsilon r equal to 2, log to the base 0.01 minus r by r. Right? This value is not known, so exchange these two values. Bring this value in the numerator, bring this value in the denominator, so that log 0.01 minus r by r equal to this value, right? Now we can simplify this. So while simplifying, what we got? 2.78 log 0.01 minus r by r equal to 2.78. So based on the previous value, we can interchange these two. E power 2.78 equal to 0.01 minus r by r, right? So the value of e power 2.78 is 16.119, that is equal to 0.01 minus r by r, right? Now multiply this r in the numerator. So 16.119 r equal to 0.01 minus r. Bring this minus r in the left hand side. So that 16.119 r plus r equal to 0.01. So 17.119 r equal to 0.01. So that r equal to 0.01 divided by 17.119. Right? So by simplify this, what we got? 0.00584 meter. That can be written as 0.584 into 10 to the power minus 3 meter. Right? So for epsilon r equal to 2, we got the value of r, that is the size of the conductor, is 0.584 into 10 to the power minus 3 meter.